We are the Sooner Rover team, an interdisciplinary team of engineers and scientists from the University of Oklahoma focused on training, outreach, and innovative design, and we are excited to present Remy, this year's Rover. The rover communicates with mission control over a 2.4 GHz antenna capable of transmitting over a kilometer through obstructions. An NVIDIA Jetson powers a flexible video streaming program that allows the operator to quickly reconfigure the display for the current mission. Custom control programs allow an operator to rapidly switch modes of operation on the rover. A microcontroller in the e-box receives UDP packets and then writes PWM to each wheel for speed control. Each wheel contains an independent power system to provide sufficient charge for each mission.
In the fine manipulation mission, the operator must perform precise movements using cameras and control UI to complete each task, necessitating minimal latency. In order to achieve this, the ARM uses multiple microcontrollers to split computation. It receives control data through UDP packets from mission control and then converts it to CAN to communicate data throughout the ARM while mitigating high-frequency noise. Inverse kinematics allow the user to manipulate multiple motors simultaneously, while PID is used to ensure the ARM functions as the user commands when load is applied. The combined use of these algorithms provides a very intuitive and responsive control scheme, making fine manipulation much easier than previous years.
This year, we focused on improving reliability and precision from the base up. The ARM rests on a widened base platform and is driven via sprocket. This allows for greater stability to improve operator control while still delivering the necessary power to rotate the ARM and any payload. A series of 2 linear actuators provides reach and strength to move the bicep and forearm members. An updated pitch drive utilizes chain to move the wrist up and down in small increments. The pitch motion is also used to interact with switches. Finally, the wrist is made up of several subassemblies. The 360-degree drive and reinforced slip ring assembly allows the rover to rotate continuously without damaging wires to assist in tasks such as turning the Allen key and positioning. The claw pinches with opposing Acme screws that hold objects along the central axis. Spanning over 14 centimeters, the claw can easily grasp tools, handles, and ropes. For heavier payloads that require less precision, hooks mounted on the forearm allow the rover to lift and carry any object with a handle.
Remy's unique Marzocod design allows it to navigate difficult terrain with ease. Each axle of the chassis is able to rotate independently, enabling Remy to traverse obstacle courses smoothly by maintaining constant contact with the ground. The large conical wheels allow for self-contained electronics, while the fins allow the rover to climb over large obstacles. The chassis' low center of gravity enables Remy to safely ascend and descend steep inclines. The wheel fins and Grousers add traction to assist in navigating various inclines, and combined with the strength of Remy's arm effector, we are able to tow a rope under a variety of circumstances.
The science package and testing methods have been redesigned to meet the requirements of this year's mission. A forward-mounted camera array allows the operator to view the site and samples. The carousel has been redesigned to hold the new sample containers that can be utilized for both chemical and microscopic analyses. Regolith is collected through the vacuum system and deposited into the sample containers on a rotating carousel. A USB microscope has been installed and calibrated for maximum effectiveness in analyzing regolith or soil samples for the presence or absence of extant life. A linear actuator allows the operator to adjust the focal distance of the camera for maximum focus on the samples.
Using GNSS, the rover is capable of calculating its distance and bearing to a given set of latitude and longitude coordinates. Using a PID algorithm, the rover adjusts its path along the way to the destination. When within 3 meters of the coordinates, the rover flashes its LEDs green. To detect Aruco tags, Remy utilizes a 150-degree field of view HUD-LIGO camera. Using a combination of the OpenCV Aruco library and a custom instance of the YOLO detection model trained with a darknet for Aruco markers, Remy can gauge the distance and angle to any Aruco tag within a frame. While on track to a set of coordinates, Remy will actively search for Aruco markers. When a marker is detected, Remy will align itself with the center of the tag. While on track to a destination, the rover uses a PID algorithm to adjust its heading with the center of the marker. From this perspective, one can see how Remy is capable of traversing through gateposts. By finding both markers and then calculating the point between them, Remy can ascertain its distance and heading to that point, then traverse through the gate.
Remy is the Sooner Rover team's fastest, strongest, and most capable rover yet, and we can't wait for the University Rover Challenge 2023.